Okay, so the last thing to talk about from this unit is when you have an experiment, an observational study, a survey, what kind of conclusion can you make and who does it apply to? So that's mostly what we're going to talk about today. And then there's one little last piece of experiments that we need to talk about. So let's start with scope of inference. Okay, so scope of inference refers to the type of conclusion that can be drawn from a study. So that's what inference means. We've talked about with stats, you want to know something about the population, but you don't have the time, the money, the effort, the energy to study everyone, and so you study a small sample. And what we hope to do is from that sample generalize to the population. That generalization is called the inference. And so we want to know who does that inference apply to and what kind of inference can we make. So the kind, like who it applies to and whether or not we can show cause and effect, is determined by two things. Were the individuals randomly assigned from two groups, and were they randomly selected from the population? I want to be clear about this. These two randoms are completely different. So they both say random, but they have completely different meanings. One is randomly assigned, one is randomly selected. So one is how we chose the subjects, the other one is what we did once we chose them. If we randomly assign people to groups, what that's called is an experiment. A randomized experiment. So randomly assigned to groups is an experiment. What that means is if we do have an experiment, we can show cause and effect. If we did not randomly assign to groups, we cannot show cause and effect. Now, how were the individuals chosen? Were they randomly selected from the population? The other option is they were volunteers. If they were randomly selected from the population, we can generalize to the population. If they were not randomly selected from the population, then we cannot make a conclusion about the population. It is pretty rare to have a random selection from your population. That's pretty rare. Most of the time, you're only going to have volunteers. So let's look at this first example. Many students insist they study better when listening to music. A teacher doubts this claim and suspects that listening to music actually hurts academic performance. Here are 4 possible study designs to address this question at your school. In each case, the response variable will be the student's GPA at the end of the semester. Here's what we care about. For each design, suppose that the mean GPA for students listening to music was significantly lower than the mean GPA of students who didn't listen to music while studying. What can we conclude? When it asks us what can we conclude, what I'm really asking is, can I show cause and effect between the listening to music and the lower GPA, and who does my conclusion apply to? So if we look at the first design, all students in your AP Stats class participate in the study. We ask them whether or not they study with music on, and we divide them into 2 groups based on their answer. So first question, were these people randomly selected? No. So our conclusion does not apply to all people or all AP Stats students. It only applies to these people. And then on top of that, were they randomly put into groups? No. They chose whether or not they wanted music. So in this design, we can show that listening to music is associated or correlated with the lower GPA. So in parentheses, what I'm saying is we can't show cause and effect. So listening to music is associated with lower GPA for these students, or ones like them. So if we don't have a random sample, our conclusion only applies to those people, those volunteers, or people like them. And again, that's because we don't know that these students are representative of all AP Stats students. So then if we look at the second design, select a random sample of students from your school to participate in a study. Ask them whether or not they study with music on and divide them into 2 groups based on their answer to this question. So what changes? What are we now able to do in this second design that we couldn't do in the first one?
Say the whole population.
Okay, we can generalize to the entire population because we have a random sample. So we can show listening to music, is associated, again, or correlated with the lower GPA. So again, no cause and effect for all students at this school. So we can generalize to all students at this school. Okay, we're going to do one more, and it's the third one. Get all students in our AP Stats class to participate in a study. Randomly assign half of the students to listen to music, and the remaining half to abstain from listening to music. What can we show with this that we couldn't show before?
Cause and effect.
Cause and effect, because we randomly assigned them to 2 groups. So we can show that listening to music causes a lower GPA for these students or ones like them. You're not always going to see the word cause, so you're sometimes going to have to read that into cause is what is being implied. Okay. Questions for me? No? We're okay to move on?
Assuming forage would be like 2 except causes instead of correlates.
Correct. Okay, so let's keep going. Next page. We're going to move on now and talk about one last piece of designing experiments. Many students enroll in prep courses to improve ACT or SAT scores. 20 students who have taken the SAT once volunteered to participate in an experiment comparing online and classroom prep courses. What you're going to do in a minute is you are going to do questions 1 and 2. You are going to design a completely randomized experiment to compare online and classroom SAT prep courses. So based on what we did 2 days ago, you need to tell me, I have these 20 students, how am I splitting them into 2 groups? And then what are you doing? Right? What are you doing? What are you going to measure? What are you holding constant? I'm going to tell you specifically that you have to use a random number generator. So I'm telling you, you can't use the hat method. You have to use a random number generator to split these into 2 groups. I'm going to give you 5 minutes. So take 5 minutes with the person next to you. What I care about most is how are you randomizing them, and then what are you doing? Good luck. Does anybody have the confidence to tell me how they randomized a number 1? Kanan?
Assign all students a number 1 through 20, ignore repeats, then generate 10 random integers between 1 and 20, and assign them to an online SAT prep course, and assign the other half to a classroom SAT.
Okay, that's beautiful. What I'm looking for, everything that Kanan said, thank you. Number the students, 1 to 20. A lot of times people will say, generate 10 numbers. If you noticed, Kanan said, generate 10 numbers from 1 to 20. You have to give the bounds. And the other thing he said is skip repeats, which is very important. And then he made sure to tell me what to do with those 10 numbers. Those 10 students are in the online course. The other 10 are in the in-person, the classroom course. Okay, here are some ways that students mess this up. First way, students will say something like, give every student a number 1 to 20. Odds get online, evens get classroom prep. Does that work?
Me and the person I was with fought that at first, and I was like, no, that's just taking,
Is that random?
it's only random
No.
in order you probably gave them the numbers, which, who knows
Right.
how that happened.
That's not random. The other thing that people will do sometimes is they only use 2 numbers, 1 and 2. And I got this question up here. They will say something like, number 1 represents online, number 2 represents classroom prep. And I'm going to generate a number for each student. You can do that one way that's correct, one way that's incorrect. The way that would be incorrect is if I started with the first person and I generated a number 1 or 2, then I did it again. Do you realize at some point you're going to have given out 10 number 1s or 10 number 2s? Right, so let's say that at the point I get here, I've given out the number 10, or I've given out the number 1 10 times. If I then say, well, everybody else is a number 2, that's not okay, because that's not random.
Yeah, that's just.
I've randomized for these people, but I haven't randomized for these people. So instead, if you just generate a number 1 and 2 for every single person, that's okay, that's random. What is the only slight downside to that?
Groups may not be even.
The groups may not be even. Now, maybe you don't care. That's fine. You don't always need to have random groups. Did we get to the further part in designing the experiment? Or did we at least talk about it? So we have our 2 groups, then what are we going to do? What are some things we can hold constant?
Well,
Like some things we can control.
Like the amount of time in the class and the amount of time that they study outside of class.
Okay, so maybe they all spend 1 hour studying every week for SAT, whether it's in class or online. What else can we control?
Say that they have the class at the same time and the test at the same time.
Yeah, exactly. They all take the class at the same time. Maybe they use the same book. What are we measuring?
scores.
Okay, scores. Did you all take into account the fact that they've already taken the SAT?
Oh, they already know what they're doing.
So what I would do is I would say like something like after 6 weeks they take the SAT. Wouldn't it be better to look at the improvement in their score then? The growth?
Actually,
That's what
yeah.
we'll compare. Okay, are we okay with that? Designing an experiment, that was nothing new. Here's the new part. What happens if we now know among the 20 students that 10 are in pre-calc, 6 are in algebra 2, and 4 are in geometry? What problem could this potentially cause?
Students with like higher education might tend to score higher than like students that don't have.
And using it in a completely random thing, meaning there's a good chance like all 10 pre-calc people end up in one of the groups, while the other 2 end up in while the
Yes.
other 2 groups end in another. And using a stratified thing wouldn't work because then it wouldn't be completely random.
Yeah. Isn't it possible that with our randomization, many of our pre-calc kids could end up in the same class? So then it's possible that there's a difference in the scores. Could be because of how they did their prep. Could be because of what class they're in.
And I couldn't think of a way to control that.
Oh,
other than
it's a good
not
thing that's
making
what
it
we're talking
completely
about.
random.
What is that called? That variable that kind of sneaks in? Confounding. It's a confounding variable. Okay, is it okay that I didn't write anything down? We just talked? Okay, so how do we address this problem? There's 2 different ways. First way that we can address it is we can eliminate some of the students. So we could not use the geometry and the algebra 2 students. So we could just say we're only using the 10 pre-calc students. What is the consequence of saying we don't want to use geometry or algebra 2?
Smaller sample.
Smaller sample. What else?
And like the sample only reflects the growth for pre-calc students.
Okay, so then we can only make a conclusion about students in pre-calc. The terminology for that is it limits the scope of inference. So whenever you see that, that's what we're talking about. We limited who we can make a conclusion to. The last thing that is new that we're going to talk about the rest of class is what is called blocking. If you had listened to what Luke said before, Luke said something like, I thought of stratifying. Do you remember stratifying with a survey? We take our people, we break them into homogeneous groups, and then we take a sample from each group. Blocking is a similar idea, but for experiments. So it's basically like stratifying. I'm going to talk for like 5 more minutes, and then we'll take a break. Is that okay? Okay. So here are the results of the experiment. You can see for each student, it tells us, are they in pre-calc algebra or geometry? What class or what treatment did they get, and what was their improvement? We are not actually going to make a dot plot, so just look at the next page, please. Here are 2 dot plots. So what you're going to notice is I want us to first just ignore the different symbols. If we just look at these dot plots as a whole, it looks like the difference in improvement is pretty small. If we just look as a whole. Maybe it went from 40 to 60, about. But now, if we block, that means we're looking at the results individually. So the blue squares are geometry. So we can see, yes, there was an improvement for geometry. These circles are the kids in Algebra 2. There was an improvement there, and then these are the students in pre-calc. The purpose is not to look at all 3 groups separately. So like in stratifying, we're not going to look at all 3 groups separately. We're going to put their results together. So that's the idea. Let's fill out these questions at the bottom, and then we will take our break. The benefit to blocking is that it accounts for sources of variability. Just like stratifying. It is another way to control a confounding variable. Less variability, the reason that's important is if we have less variability, that increases our chances for finding convincing evidence. Like convincing statistical evidence of a difference. We're going to write down 2 more questions and then we'll take a break. In general, how do we determine which variable is best for blocking? Same way we did with stratifying. We are going to choose a variable that is strongly related or the best predictor strongly related with the response variable. The subjects or the units within the block, each block, should respond similarly. But different than the units in other blocks. So within each block should be similar, but those units should be different than the people or the units in a different block. Okay, The only difference between blocking and stratifying is when you use that term. Blocking is only used for experiments. Stratifying is used for surveys. That is the only difference. Okay, so let's keep going. If we look at this next example, a popcorn lover wants to know if it is better to use the popcorn button on the microwave or use the amount of time recommended on the bag of popcorn. To measure how well each method works, she will count the number of unpopped kernels remaining after popping. She goes to the store and buys 10 bags each of 4 different varieties of microwave popcorn for a total of 40 bags. Outline a randomized block design for this experiment. Okay, we're not actually going to go through the whole process. I'm just going to talk about what we would do. So we would take the 10 bags of movie butter and split them up into 2 groups. One group being microwave and one group being the amount of time on the bag. Then we would take the 10 bags of light butter and we would break them up. The time on the microwave, or the microwave button, time on the bag. And then the 10 natural. Again, use the microwave button, use the time on the bag. So on and so forth. We get the idea? Okay. And then you'll just go about the experiment like you did normally. When you are randomizing, you do not need to describe the randomization 4 different times. Describe it in detail for 1. So I would say something like, I take the 10 bags of movie butter popcorn and number them 1 to 10. Use a random number generator, blah, blah, blah. And then you can just say something like, repeat the process for the light butter, and then for the natural, and then for the chemical. Make sense? Are you okay that we're not actually doing the whole process?
Yes.
Just a little bit on the vocabulary. Notice that this says randomized block design. You could also just be asked for a completely randomized design. A completely randomized design is just a regular old experiment where you're not blocking. I will tell you, I only block if I'm told to. So if I'm told to just design an experiment, I will not block unless there's a really obvious factor to block on. You do not need to block in every single experiment. Block if you are told to, or block if you are told about another variable, like in this case, the variety of popcorn. Okay. A few other things to talk about. Next thing, a matched pairs design. This is a very specific block. So this is a blocked design where each block has only 2 experimental units. Either you are using 2 very similar people, or what often happens is that you are using the same person. So for example, probably the most common matched pairs design. Have you ever been outside in an area that has a lot of mosquitoes and there's some people that get a lot of bites and some people that don't? Okay. So if we were looking at 2 different mosquito repellents, if we just used a regular experiment, what I would do here is split you into 2 groups. Half of you get one repellent, half of you get the other. But we're really not taking into account that some of us get more bites than others. So if you used a matched pairs design, each of us would be a block. One arm would get one repellent. The other arm would get the other repellent. So really then you are just comparing to yourself. Does that make sense? Okay, what is really important is that this is still an experiment, so you still have to randomize. So I cannot say everybody uses repellent 1 on the left arm and everybody uses repellent 2 on the right arm. That is not randomized. We would have to choose the arm randomly for every person. Make sense? Okay. So if it's the same person, we still need to randomize. Okay. We have two last things that I want to talk about, and then we are done with notes for the day. Okay. Last thing before our last example is this idea of statistically significant. What statistically significant means is that any difference, thank you, found in our study is unlikely to occur by sampling variability. Okay. Here's what I mean by that. Let's say that we want to compare the amount of time that students spend on homework for PHS students versus Hersey students. And let's say we take a survey from each of those groups. And let's say at PHS, the amount of time on average that students spend on homework is 47 minutes. And at Hersey, the amount of time is 49 minutes. And so our study is concluding that in general, students at Hersey spend more time on homework than students at PHS. Now, do we know for sure that that's the case?
No.
Is it possible that we just happened to randomly choose students at Hersey that spend more time on homework than we did at Prospect?
And there could be any number of confounding variables.
So there's
like
confounding
differences
variables
in
and
curriculum or teachers.
Okay.
And
Yeah,
there's
if we
many-
take all of those confounding variables and we ignore those, there are confounding variables we need to think about. What we would do, we can't do this yet, but we will do it, is we would figure out how likely is this difference to be? How often would it occur if we're just randomly choosing students? If it would occur 50% of the time, that's pretty likely. But if this difference only occurs 2% of the time, we would call that statistically significant. This difference is unlikely to occur just by variability. And we're going to take a look at this last example. This is the last thing that we are going to do in notes, and then we will probably go over your test and go over your homework. Okay. Last example. Over the years, the percentage of births that are planned C-sections has been rising. Because doctors can schedule these deliveries, there might be more children born during the week and fewer born on the weekend than if births were uniformly distributed. To investigate, Miss McDonald and her class selected a simple random sample of 73 people born since 1993. Of these people, 24 were born on Friday, Saturday, or Sunday. To determine if these data provide convincing evidence that fewer than 3/7 of people born were born on Friday, Saturday, or Sunday. Okay, so let's talk about that part. We are assuming that the births are evenly distributed. 1/7 of people are born on Friday, 1/7 Saturday, 1/7 Sunday, 1/7 Monday, so on and so forth. What we're asking is there evidence that less than 3/7 are born on a weekend, possibly because C-sections are being planned, and so people are giving birth during the week instead. So we are looking for evidence that less than 3/7 were born on a weekend. So we simulated 100 random samples. So this came from a computer. Each dot shows the number of people born on Friday, Saturday, or Sunday. What we told the computer is assume a population with equal chance of birth for every day. So we put into the computer every day is an equal chance of being born. Simulate 73 people, because that's what the sample was. And out of those 73, count how many were born Friday, Saturday, or Sunday. So that dot plot is just ideal world. So this dot, for example, represents one sample where 40 out of the 73 people were born Friday, Saturday, or Sunday. Does that make sense what this graph is showing? Part A, how does this graph illustrate the idea of sampling variability? Okay, so let's start talking. How does this graph illustrate sampling variability?
It shows.
Kiara?
Like even in a world with no like confounding variables where it's completely random, it's not always like 30 or whatever. It varies.
Yeah, it's just the idea that if we have the same population, when we take different samples, we're not always going to get the same result. Okay, here is the part that is most important, is B, and this is what people tend to mess up. Based on the data from the study and the results of the simulation, is there convincing evidence that fewer than 43% of people born since 1993 were born on Friday, Saturday, or Sunday? Okay, so let's think, if this were an ideal world, out of those 73 people, we would expect 3/7 to be born on a Friday, Saturday, or Sunday, which is about 31.29. So perfect world, that's what we would expect. Now, what actually happened is 24 out of the 73 were born on a Friday, Saturday, or a Sunday. So there is a pretty big difference between what we expected, that 31.29, and what actually happened, which is the 24. So we want to know how likely would 24 out of 73 or less than that be if 3/7 of people are actually born on a Friday, Saturday, or Sunday. So even if 3/7 are born on a Friday, Saturday, or Sunday, how likely is it that we would get 24 or something smaller? That's where this simulation comes in. That 24 is here. And we're always looking for that and more unlikely. So that happened 6 out of the 100 trials. So even if 3/7 were true, we would get a sample with 24 or less 6% of the time. Have we talked yet in stats about what the cutoff is for something that's considered rare? No? Okay. The cutoff for rare in stats is generally 5%. So because we got 6%, which is greater than that 5%, that 24, it's not going to happen a lot, but it is going to happen, even if 3/7 is true. So is there convincing evidence? We would say no, there is not convincing evidence. that fewer than 43% were born on Friday, Saturday, or Sunday. Because a sample with 24 out of 73 people born on Friday, Saturday, or Sunday will occur about 6% of the time in a population where 3/7 of people are born on a Friday, Saturday, or Sunday. So because this is not rare, we have we do not have strong evidence to question this 3/7. Questions for me?